Hi, my name is Fazirul and this video will be showcasing my final year project titled Simulating Distributed Consensus Algorithms Among Applications in CloudSim Plus. The title is quite long, so first things first, let me break it down to you. Distributed consensus algorithms, what are they? In a distributed system, we have a set of processes that can communicate with others. A consensus algorithm is simply an algorithm that each process runs such that all processes agree on a single value. These processes continuously exchange data until a consensus is reached. In cloud computing, applications have computing tasks to offload to the cloud. Normally, this is managed by a central orchestrator, which takes in such requests from the applications and decides which server on the cloud to offload these tasks to. The role of the centralized entity can be anything. In this example, it is for load balancing, where the entity spreads out the request across multiple servers so that the load is shared equally. Using a centralized entity is perfectly fine. However, distributed consensus algorithms can also be applied in this context. To do so, the centralized entity is simply removed and applications directly connect to the cloud. If we go back to our previous example of load balancing, without the centralized entity, all the applications could just offload to the same server, causing a server overload. Therefore, each application must exchange some sort of data throughout the network, which is specified by the algorithm implementation itself. This message exchanging process continues until an agreement is reached. The agreement here could be, for example, deciding which application gets to offload to which server. Once the agreement is reached, the applications can proceed to offload their requests to the respective servers based on the agreement that we have discussed. Now that we have discussed what are distributed consensus algorithms, let's talk a bit about CloudSim Plus. CloudSim Plus is an open source simulation framework that is widely used within the literature. It allows researchers to focus on specific system design issues to be investigated without focusing on the low-level details of the cloud. The main motivation driving this whole project is due to the fact that CloudSim Plus does not have implementation support for the algorithms we discussed in previous slides. As a matter of fact, this is the case for most, if not all of the computing cloud simulators available currently. Researchers who want to evaluate the performance of their proposed distributed algorithms must create simulation scenarios from scratch, which is a time-consuming effort. Therefore, back to our title. The goal is to extend CloudSim Plus to simulate distributed consensus algorithms. Now I will give a demonstration. Welcome back to the project demonstration. This project uses Java, which is the language that CloudSim Plus uses. Now I won't be going through the code for this demonstration because I just want to show an example of how the simulation will run. So I have this example here and let's run it and see what happens. You can see on the terminal that log statements were printed, and these log statements show how the system changes as time progresses. For example, you can see that at time 7 seconds, application 1 is trying to create a virtual machine in server 1. At the end of the log statements, we can also see that there are some statistics collected about the system. Users are free to define what kind of statistics they want to collect. In this example, we are collecting, the total number of messages exchanged as the distributed process is running, as well as the average convergence time of each application. Before I move on, let me share with you that this example is actually using a distributed consensus algorithm called Dragon. You do not have to know the specifics of Dragon, you just have to know that Dragon is a distributed consensus algorithm that we have discussed in previous slides, and also that it is implemented for this example. Now, this project provides the flexibility to users to define the kind of entities they want in the system. For example, users can define the number of virtual machines as well as the resources demanded by each virtual machine, and the same goes for the edge devices and the edge servers. Additionally, users can define the arrival times of each application as they enter the system. Right here, I have another example called visualization. So this example is the same as the one that we've seen before, but additionally, it runs a visualization tool that this project created. And the visualization tool shows how the system changes as applications leave and enter the system. You can see that just now, some resources were used on nodes 1, 2, and 3. So those were the features of the extended simulator. More details can be found in the documentation and the code. If you recall, in the demonstration, I have mentioned that we are able to collect statistics of the system. We can then evaluate the performance of algorithms objectively using such statistics. So one statistical method that can be used is the paired t confidence interval, as you can see in the slide. Suppose you want to decide between two systems. System 1 could be using the Dragon algorithm, while System 2 could be using a different algorithm. In paired t confidence interval, for both systems, we run one simulation, tabulate the metric, and get the difference. We repeat this r number of times and calculate the mean and variation of z, where z is the difference. The more runs we have, our evaluation becomes more accurate. In this case, we have 5 runs, as you can see in the table, and this table is just an example of statistics that I have collected in my experiments. So with an alpha value of 0.05, where the alpha value represents the confidence level, the interval calculated is from negative 0.14 to negative 0.02. From these example data points, we can conclude that Dragon is better than the alternative algorithm in terms of convergence time, since the interval lies completely to the left of 0. We have now come to the end of this video. Thanks for watching.